Hello everybody, welcome to my programming club. Today we will be solving another daily lead code challenge, and the challenge's name is hold the nodes at k distance in a binary tree. Given the root of a binary tree, the value of the target and the value of the target node and an integer k, return an array of the values of all the nodes having distance k from the target node. You can return the answer in any order. So the order of the answer doesn't matter. So what's the problem statement is saying that, for example, if we took this example, and paste it here. So if we consider this example, but the problem statement is saying that it will be giving us a root of the binary tree. Currently this is the root. This would be given, and the target will be given. Here in this particular sample test case or example, the target is 5. The node with value is equal to 5. So this is the target, and what the problem statement is saying that an integer k will be given. Okay, and integer k's value is 2. K's value is 2. What we have to do is we have to return an array of the value of all the nodes that have a distance k from the target node. What it means is, if target node is this, then we have to return all the nodes at a distance k. K is here 2. So 3 is at distance 1. 1 is at distance 2. 6 is at distance 1. 2 is at distance 1. 4 is at distance 2, and 7 is at distance 2. So you can also see that these two distances or k distances k distance nodes are marked blue also in the sample test case. So these are what we are required to return as an answer, and the order doesn't matter. You can return 741, 147 or in any order, in any particular order you may like. Okay, so how we will be approaching this problem? If we simply look at the problem statement, it's saying that we have to return all the nodes at distance k from target. So if we do a normal traversal, depth first search traversal of a tree, then it will always go in this direction, either this direction or this direction, for the given target, but it will never go in this direction because there is no link between its parent of target or of any particular node you are considering as of now while finding the kth distance node from the target. For example, you can go from 2 to 4, but you cannot go from 4 to 2, not directly by recursion stack. By recursion you can go, but there is not a direct link between 2 and 4. There is a link in opposite direction from 4 to 2. This is a link going downwards from 2 to 4, but this link is not there. This link, oh, let me change the color again. I think this link is not there. For example, here you can go from 2 to 7 from a direct link without help of recursion or anything if you have address of 2, but you cannot go from 7 to 2 as the link is not there for visiting 7 to 2. So what we would be doing is we would be inserting those links. What I am saying is we would be making the tree bidirectional. Or tree is a graph in itself without a cycle. Tree is a graph without a cycle. So if we just make these edges bidirectional, by bidirectional I mean you can go from 2 to 4 and 4 to 2 by these direct links. So all of the edges will be becoming bidirectional. After we are make all the edges bidirectional, now it's very easy for us to find out the distance, k distance nodes from the target node. For example, it would be just using BFS, breadth first search. We can easily find the distance, kth distance node from the target node, because BFS would find all the nodes at kth level if our target node is considered source. What I mean to say is, for example, if you consider 5 as a source from where we will be starting our BFS, this is level 0, 0th level, and then neighbors of 5 are 6 and 3 and 2. These are at first level, and the neighbors of 6 are none, and neighbors of 3 are only 5. We have already written. We want to be the thing is that while doing this BFS traversal, we want to be going upwards. We want to be going to the parent, the current node. So we would be keeping check for that. I will explain that in coding part. I will be preventing going backwards. Then our 3 is another neighbor is 1, and 2's neighbors are 7 and 4. So these all are at second level, or you can say they are at k distance apart from the from 5 because you can see 6 3 2 are one distance apart from 5, and these nodes are at two distance apart from 5. So this would simply be a BFS, and for making these links, let me quickly take our new slide and copy that example test case again. So to form these extra links, bidirectional links, what we would be doing is we will simply be going in a DFS manner, and we will simply be adding these extra links. How we will be adding these extra links? That I will explain in the coding part. So you may ask, why can't we go in a BFS manner and then add those links? It's also possible, but BFS will be using more space. Since in DFS what happens is that if you, let me quickly change the color, if you go from this direction to this direction and you hit the end, you traverse back, and all the entries in the recursion stack, that would be like, if you are going from 3 5 to 4, it will be 3 5 2 4. They will be popping out one by one. 4 goes out, then 2 goes out, 5 goes out, then 3, then again you will be traversing a new branch. 3, actually 3 will not go out, 3 will stay. And then for the left part, for example, if you are traversing this, then 3, then 1, then 0. Now we hit the bottom again, then this goes out. And eventually when all the branches from 3 are traversed, 3 will also go out at the last. So what I mean to say is the recursion stack will be reused. But in case of this queue that we use in a BFS, if there are, for example, say these nodes at one level, then they will be in the queue. It would not be the case that only the current paths nodes are in the queue. So it will generally take up more space, so that's why we are preferring DFS. So let's move towards the coding part. So what I have done is, let me go to the main function. I have declared a graph. Actually, we will be converting this whole tree, this whole given tree, in a bidirectional graph. Bidirectional graph. By bidirectional means every edge does not have any particular direction. You can either go from, if there is an edge between U and V, you can go from U to V and V to U. Both way are allowed. Okay, this is for converting the given tree in a bidirectional graph. Then we will be doing DFS. This will be for making tree a directional graph. This is the part where we will be adding the links. So what we are doing is, along with adding links, we are storing the given, we are finding the target node in the tree, target node, which we would be using when we are doing this part of the program, when we would be finding the nodes at the kth distance. For this part, we would be needing the address of this node. So while adding links, we will also be finding this and storing it in a global variable. So please ignore these comments. These are just for the debugging part that I was doing while solving the problem. And then moving towards the link making part and finding the target node and storing its address. Here we are storing the address of the target node. If the current node is equals to the target, then we will simply be storing its address. And then we are, in this part, we are making edges, the bidirectional edges in the graph, and then we are doing simple recursion to make all the bidirectional edges in the tree and converting it into a bidirectional graph. Then what we would be doing is, once we have a bidirectional graph, then we will be initializing a result variable, result list, that we have to return for the nodes at the k distance from the target node that we have just found out, whose address we have just found out while making the graph the bidirectional, while making the tree bidirectional graph. Then we would simply be finding the nodes that are at k distance from the new root, or you can say new source. Then this is the BFS part, and actually for a tree, this is also called level order traversal. So we will be initializing a queue and doing a simple BFS, and we will be considering our current level as 0, and the node would be at the 0th distance from itself. The current root, the new root would be at the 0th distance from itself. And then if we have reached a level which is equal to the required distance, that is k distance apart from the new root, then we would simply be adding those nodes in our result list and would not be doing any another work. If that's not the case, then we would be doing simple BFS over the graph. And for checking that we are not going, for example, if you consider a particular edge, say you consider a bidirectional edge between 3 and 5. If for example you are going from 5 to 3, then there would be a case that now 3 is a neighbor of 5 and 5 is a neighbor of 3. So while checking out neighbors, for 3 you will also be getting 5. So what we are doing is, when we are queuing, when we are taking out any node from the queue, we are just putting it in a visited hash set, or you can say any visited asset, and then we would be avoiding it here. If it is already in the hash set, means we have already visited that node, we would not be again including it into the queue, and that's how we will be avoiding this condition going from 3 to 5 in opposite direction of the flow. So that's pretty much it, and with will be this is the standard BFS, and that's it. We would be returning the result array, or you can say the list as is required, and yeah, that's the problem and the solution. So you can see the solution is getting accepted. The code is available in both languages, C++ and Java, and it would be available on the GitHub repository, same as before. So thank you for watching. Subscribe to my channel for more such content. Thank you.